this intersection of H and H hat of Z. Let's be a little bit careful. Let's be careful. So again, for the same sort of reason, if you're just working under the not P-small condition, you have to be a bit careful. So here, I'm going to sum not exactly over H, but I'm going to sum over all of the sets U that can be written in the form H intersected with H hat Z, or some H from the family script H, where the fragment T of WH is large. And here's just P to the side of P. So the sum have to be in U, not in H. That's a more important point. Okay, so this stripe set is our set U. Well, what do we know? U always contains T, right? So U will have size at least T. In other words, I can write here summation in this way. Once I fix Z, I know what is the set H hat of Z. So I'm summing here. In Z, all of the sets U that can be written in the form H intersected with H of Z with size at least T, and I have P to the U. Every U that can be written in this form of size at least T. Why did we do that? Well, we have the condition that the family H has VC dimension at most T. So you can actually deduce that the family of sets of the form H intersected with this fixed set H hat Z, this also has bounded VC dimension. And now, because it has bounded VC dimension by Saar-Scheller, but also Wapnes-Chervonenkis, you have an upper bound, right? The number of sets of the form H intersected with H hat Z, where H comes from our family script H. This is actually at most something like L to the D. So something like L to the D, maybe E L over D to the D. It's a safe upper bound. So the standard result of our set system with bounded VC dimension. And here L is just coming from the size of the set H hat Z. Okay, so that is quite good input.
As in the smooth case, we are really fighting for locating this T. In this case, we have VC dimension helping us
Right.
limit the choice.
That's right. Exactly. So VC dimension limits potential choices for how two sets in H can intersect. Which is how we can, why we define U bar this way and why it helps. So if we use that bound, then we can continue the calculation. We can sum over large T, and we have the familiar factors. In the final factor, we can plug in that bound right there. So EL over D to the D. And when we have the sum of P to the U, where U is at least the size of T. So anyway, that is going to be at most P to the T. So we have this bound. Okay, so now you can see why we picked CD log L, right? So the main thing we need to fight here is this factor of L to the D, so E to the D log L. And we have this factor of C to the minus T fighting against it. So if we choose T to be a constant times D log L, we can guarantee that this is very small. Something like L to the minus some constant. Okay, so this is essentially the proof. Right, so we use the same thing again. We do the iteration, just as in the proof of the Kankali conjecture, or if you prefer, you can do the easier version where you run it in a spread setup. And what this is producing is it allows your fragment to shrink by a log factor in every step. So roughly after log star of L many steps, you are done. Okay, so right, so that was a few applications among this world of sunflowers or access systems, and this will so the smooth spread property in particular will be fairly useful for us in the last 2 days. And one of the points here was really, as you see in the proof, we always do the same thing. So once you are familiar with the proof of the Kankali conjecture via the minimum fragment that we saw, and in particular just this one non-trivial step where we do this change of probability measure between W and Z, then all of these applications will fall in a very streamlined fashion. So, well, maybe for the last few minutes, we can take a break at this point anyway. I'll mention briefly the last application, which is of a different nature. So it's an application of this short version of the selector process conjecture that I mentioned, which is a somewhat of a more abstract statement. So again, the theorem statement there, you have H, which is not P small. And then some adversary can come in and then give you all of these weights or coefficient vectors, whatever. You have the condition that the sum of the weight is at least 1, let's say equal to 1. And then the conclusion is that with reasonable probability, if you sample a random subset with density Cp log 1 over epsilon, then you sum up the weights inside some set H from your family, you get at least a 1 minus epsilon fraction of the weight. Okay. So what is the application I want to tell you about? Again, this is regarding conjecture of Talleyrand. So in defining and imposing the fractional expectation threshold, he conjectures actually that the fractional expectation threshold is always equivalent up to some constant to the expectation threshold, which is by itself fairly magical statement, because this expectation threshold and fractional expectation threshold are very general, define very general context, and in general is the relation between a linear program and an integer linear program and its relaxation. And Talleyrand's conjecture somehow suggests that for this vast family of linear programs, there is always this, essentially only this small gap between the integer problem and the relaxation. It's fairly surprising. And again, somehow, Talleyrand has an extremely rich and wonderfully broad picture regarding all of the intricate phenomena here. So we still don't know a full resolution of Talleyrand's conjecture. And before we know quite limited cases of the question, but now let me tell you one of the corollary that you can prove with it. So really, this statement you can equivalently state as the statement that if H admits a fractional cover W that is small, in the sense that the sum over W of P to the side of G is at most 1/2, then you can also construct an integral cover but now with the sum of P divided by some constant potentially raised to the G at most 1. So it's something about being able to round a fractional cover to an integral cover. And what we know is now is that if H has a fractional cover W with small count, and W is supported on sets of psi at most T, then H has an integral cover that is P over log T. So we can round fractional covers to integral covers, but in this rounding procedure, we do lose this log T factor in the uniformity of the fractional cover. We do know though that if the fractional cover has quite large uniformity, like log N, then result Fisher and Person shows that we can round the fractional cover quite efficiently. So this at least is speaking quite well about the complementary range, even though this log T factor doesn't allow us to completely resolve the conjecture of Tullacre. And okay, don't think I will have time to tell you about the full proof. So I'll just tell you that the proof idea is actually fairly simple. So what you do is you assume that H is not Cp over log T small. Well, I want to use the sharp version of the selector process conjecture, so I need to set up some weight. But there's a fairly natural notion of weight that you can use here. So for instance, you can just take the weight lambda H of an element X in H to be, well, the sum over all of the sets W fitting inside H that contains this element X, the weight, fractional weight of W in the fractional cover. The right way is to do this, and then normalize it. Okay. And once you take the conclusion of the sharp selector process conjecture over there regarding to this weight, then you can deduce a contradiction against the statement that W is a small fractional cover. Okay. So there are about 2 minutes, so I think I will unlikely be able to tell you a lot about some of the ideas behind how one can prove either the original version of the selector process conjecture or this sharp version of the selector process conjecture. Actually, I should also mention that there is also a later paper by Bednorz, Martinek, and Miller, where they give some simplifications to the original proof of the selector process conjecture, and they extended more in the probabilistic context to other classes of stochastic processing. Now, at least maybe just a single word about how you may at least start proving these results. The proof in a very high level will be still fairly similar to how we prove the Kankali conjecture. Actually, that's how the Kankali conjecture is almost a subset of that proof. You do it appropriately. What you need to change in your perspective is to think about redefining the minimum fragment in a somewhat different way. So originally, when we define the minimum fragment, which has a very simple definition, turns out in this context, the better set to start with the definition is not the minimum fragment, but the set Z and the notion of feasibility for Z. So for example, for the selective process conjecture, it turns out that the right notion to use is to say that a set Z is feasible if there exists, okay, some H from the family H and set W in Z such that the following property holds. So, okay, now this is a bit definitely too short of a time to tell you what happens here. So what you need to do is to, well, first, for every H from the family script H, let's order the elements of H according to decreasing order in the weight. So let's order them so that lambda H of H1 increase lambda H of H2 all the way until the last element. I'll define a special index for every W. We can define a special index B of WH. So this should be the smallest index so that we can still guarantee that W captures a large fraction of the weights in the tail segment. So such that the sum over J bigger than B of lambda H of Hj, indicator Hj is in W. This is still at least a constant fraction of the sum over all of these lambda Hj. Okay, so somehow for the tail, we can guarantee that W catches at least a good fraction of them. And because W already quite successfully captures the weight of the tail segment of the set H, what we want the set Z to capture is not that tail segment, but just the original segment. So such that Z contains H1 up to HBWH. So this turns out to be the right definition for feasible H, and then your minimum fragment T is the usual way. So this is the minimum subset of H such that W union T is feasible. And then one can trace through carefully in order to do the same key property encoding swap the order of the summation in order to prove the original version of the selective process conjecture. And for the sharp version, it's going to be even more complicated. So the notion of the main thing that one needs to write down and understand is just the notion of feasibility. And in the end, what we will have enough is not the minimum fragment, but what I call in the end the tower of minimum fragments. So if you are interested, you can take a closer look in the paper. That's all. I'll take some questions.
So these things for the sunflowers, they actually wouldn't work if we would want to have a sunflower that has a non-trivial center. Or
So
because
the original pre-processing step, I guess, already put something into the center. Right, there's this simple greedy procedure at the beginning where we put things into the center.
but it couldn't happen that you sort of directly jump to.
Yeah, but it could happen that originally at the beginning you are already spread, and then anyway, there's no guarantee that you would have a sunflower with a non-trivial center. For example, all of the sets could be disjoint from.
But is there are there some bounds? Is there some conjecture? I guess they would also depend on the size of the center.
Yeah, then that may depend on the crowd set or some additional condition that you put on the set system. So I'm not sure if there's one that guarantees the non-trivial center.
It's the bond in after, sorry, I'm talking about some problem. It's the bond after pre-processing, assuming the spreadness is that bond not height, is also contributes to CR to the footer.
Oh, so you are
So
asking,
I'm just asking if I want to find like disjoint sets and assuming the square net.
so no, so we only know that the bound is tight if the only way that you want to find a disjoint set is by random sampling. Is to do this trick of random partitioning and random sampling and try to find a set in there. That's where we know that that bound is tight. But if you are allowed to carefully search, then we don't know if that's tight. Maybe it's still constant to you. And right, in fact, there's some conjecture of Tanaka which may suggest that it should be true that once you go beyond random sampling, you may just need this constant 2DL in order to get the disjoint cells. It's essentially.
So there is some questions in the chat. One question is, in the application of sunflower, spreadness looks like pseudo randomness for set system. So can we find some similar forms of spreadness for set systems on the flip, or maybe some whole abelian groups?
Some
Some form of spreadness for abelian group, something related to.
yeah, so actually some formal notion of spreadness in abelian group. So yes, and so the same spreadness property. So indeed, it's a correct observation. The spreadness is a form of a pseudo-random kind of property. It actually also appears maybe under some different name in the study of hypercontractivity and the various different types of domains. So they got already might find some different generalizations of it, but also kind of the same spreadness property appears in works around set avoiding three-term arithmetic progression. So the breakthrough by Kelly and Meka and a lot of the follow-up works. And there, indeed, it's a form of spreadness in an abelian group. So spreadness takes the form of you cannot pass to a subspace or subgroup of reasonably small codimension defined appropriately, and after which the density of the set jumps up by a lot. And that property there is kind of the key property in their work, as well as some other work on hypercontractivity, as well as.
There is another question which is in the middle of the around 10:30. I missed it. Sun Tong was asking, you still have to show that the families produced after each iteration is still p-spread, right?
Right. Yes,
This
but
is which question?
I guess it may be what after when I state the key lemma and the p-spread, then after one iteration, you can show that almost all sets produce a small fragment, and then I just take the small fragments to be my next family. These still have to be p-spread, but because they are almost all of the original set, they almost just trivially inherit the p-spread property from the original family. There's a little bit in the loss in the parameter, but one can be just careful and these don't affect much.
Maybe one more question. From Veronica asking, I was wondering for the definition of the expectation threshold, since for the graph version, this is the expecting number of subgraphs H in GNP goes from being less than 1 to growing to infinity. Why this time we consider 1/2? Could the definition also has worked if we had a 1 there, or am I confusing something in the definition?
Right, so I can maybe vaguely ask, I guess, what the question is about. So yeah, and maybe to compare to the Coase notion of threshold, this is a fairly specific threshold and everything is chosen around 1/2. For the expectation threshold, you cannot change really 1/2. You can change 1/2 to almost any reasonable parameter, but perhaps not 1, just because at 1 there is a special cover that works for every set system, and that's just the empty set. And so if you want to find the cover with cost 1, then it always exists, and that's kind of what we want to avoid. If you now ban the empty set from the cover, then there would be some interesting stories, but yeah, so it gets interesting, and it actually appears in some of the recent works connecting these type of phenomenon to hypergraph container, but might be too long a digression at this point.
So maybe let's think way for.
Recording stopped.
Double check again.